Yeah, so thank you for having me here. And I would like to present a framework to estimate dynastic life cycle models. And hopefully I'll have enough time to go to full-blown application in the second half of the talk. And if you are planning to attend the conference, I would add like market equilibrium and strategic interactions within families into this framework. So why do we care about it? So so you have a large literature now on inequality and the sources of inequality, and families are important. And so we think that altruism and intergenerational link and investment in children is important to understand inequality. And especially if you want to do policy analysis, it's important to model intergenerational link explicitly. And, there is well-documented large persistence in education, income, and wealth outcomes. And again, we'll focus on parental investment and transmission of human capital, at least in this talk. But the framework is general enough to incorporate bequest and monetary transfers as well. So the life cycle, so the complication here is that it's an infinite horizon model. If you think about Barrow-Becker type of models, right? So people care about the utility of the next generation is in the utility function of the current generation and vice versa. So it's an infinite horizon model, but within a life cycle, but we incorporate life cycle, which is non-stationary. So you have the standard, life cycle models that are finite horizon, and then it's incorporated within infinite horizon models, and that complicates estimation. And we want to think about sources of lifetime inequality and transmission of inequality and mobility within this framework. And we want a lot of decisions to be accounted for explicitly. So that is, they're endogenous. So for example, fertility. So you have a lot of studies on about quantity-quality trade-offs of children, and labor supply, investment in children, savings in general, bequest, all those are decisions that you might want to account for endogenously, depending on the questions that you're going to answer. So the goal of the first part of the talk is to develop an estimator for dynastic models. And of course, the challenge is that computationally they become infeasible very quickly. And it's going to build on things that you've seen in previous lectures. And we're going to develop a step estimator. And for discrete choice model, in the paper that I'm building on, there is an extension to have also continuous choice, but I'm not going to be able probably to get to it today. So I'm going to talk about, in the application, we'll have altruistic unitary life cycle model of household transmission of human capital across generation with endogenous fertility, and labor supply is also going to be endogenous. Let me start presenting just the general framework. So, the problem is going to be a discrete Markov decision process. And we're going to have a representation in terms of valuation function, the standard one. You could do a full estimation or nested fixed point algorithm. But that would require solving the valuation function for each parameter value and search them, and it becomes really quickly infeasible in this type, or at least in some types of models that you might want to be incorporated. So the other proposed solution that you've seen probably in previous lectures is that have the representation of the valuation function in terms of the model's primitives, the utility function parameters, the conditional choice probabilities, and the transmission function. So that would be the goal here. but the structure is a bit different from Hotz-Miller representations, the Hotz-Millerish type of representation, which you could have for infinite horizon models or finite horizon models. And here we kind of have both structures. That's the goal. So the first part of the talk, I want to go and develop the representation and then go and to a full-blown application. We're going to have stationarity assumption over generation. Of course, within the life cycle, the problem is non-stationary. And sorry. And the estimation is going to be done by pseudo maximum likelihood or GMM estimator. For a simple problem, we did pseudo maximum. We did both in the paper, but we're going to do. But I'm going to present a GMM estimator later on. Sorry. So let me start with a generic genderless model. So, sorry, I've been a bit under the weather. So each generation lives for cap T periods.
I found this on the web.
Well, sorry, it is on the web. No. I mean, just break for 30 seconds. I've been sick since I got here. Sorry. So we have a life cycle within each generation. And there is, sorry. Can we take just, can I take like just a minute break too?
Yeah, take a break.
I may need that. Maybe I'll have time to read the slides. Okay. So we have cap T periods, that's the life cycle. And then you have infinite horizon in terms of generations. And each period, parents are going to make decisions about fertility, labor supply, and time spent with kids, and monetary transfer. And the main model is transfers of human capital as Lowry in 81, which did not have endogenous fertility. So children consume or otherwise do nothing. Adults make discrete choices. So we have labor supply, no work, part-time or full-time. Can I take maybe like 5 minutes? Wait for you. Ready to go. So I will proceed in steps. I'll speak and then I'll take a break if I need to. And so let me just go back. Oh no, I'm going forward. Let me go back to the choices. So as I said, we have three in this model, 3 labor supply choices: no work, part-time, and full-time. And then time spent with kids, again, no time or low, medium, and high. And birth is a binary 0 and 1. So this is for, again, this is the genderless model. And an indicator IKT. So K would be an action and choice. And it's a combination of choices, right? So labor supply, time with kids, and birth at HT. So we don't have time, we just have life cycle here. So we have age, and let me define a time invariant characteristic state variable or vector. So when you become an adult here, you would have like race, skill, and education. I will tell you how it is formed within the model. And so I'm just presenting first the systematic state variables. And then you have the choices. So the choices will go past choices into the state space. So for example, how much time you spend with kids in the first 5 years would be choices. So you keep track of them, and you could have also monetary investment. But so far, it has to be so discrete here. So within all this, we have 17 choices, but this is in this example. And then you have U2, which is utility from consumption. And ZT is the state variable. So ZT is the include X and all the past actions. And we keep track on fertility because it would matter whether you had siblings and how many kids you have and at what ages. And we would have a utility, and then we have, so UCT would be utility from consumption. And then when we have non-pecuniary utility from the different choices. So you would have for each combination of choices, K, like a parameter. So that allows you to have different, this utility, let's say from working full-time, if you spend a lot of time with your kids, right? For, you know, and you have non-linearities, and this could, and then you have different disutility from working full-time when you don't have, you know, when you put no time with your kids or you don't have kids, okay? So that allows for all these combinations. So these are the state variable, these are the per period utility. So U1 KT would be the utility from the different combination of choices. And then you have the kind of standard IID taste shocks. Okay, so for each combination, for each choice, for each combination of choices, you would have a shock.
Why you make it entirely history that really increases your emission of the state variable? Why is it important to do that? Why can't you make it a Markov in the state variable?
So what I need to be able, it depends. So this is just a framework for estimation. So it depends on the application. So here I want to say that how much time, so you could, how much time, maybe at different ages, you might be able to simplify it. So how much, you know, so right now I'm allowing you to say how much you invest in the kids at age 1, 2, 3, 4. And you need, but possibly you could kind of aggregate it in a different way to simplify it.
Okay.
But we're allowing, but the framework allows for it.
Okay. Well, yeah. So you could kind of like underinvest when your kid was very little, but maybe try to compensate, but there would be damage or something that would carry through.
Correct. So this is allowed in this framework. And the standard also, we will have labor market experience, you know, with depreciation in the last couple of years and things like that. But there are obviously ways to simplify it. And then, so this is a simple example or an example. So expenditure with kids here are not going to be choice. We actually don't have data, but we're going to assume that it's a fraction of your income and it interacts with the type of household. And the type of household here would be the education composition. So we're assuming that people with different education and different level of income would spend different share or, you know, share of their income on the kids. And then we have the standard budget constraint because we have no borrowing and saving. But if you look at the paper, you could extend it to have continuous assets and savings. So that would mean that you would just plug the budget constraint, which is the wage. So this is the income. There is one genderless. This is just the household. And you have consumption plus the expenditure of the kids. And you just plug it in the utility function for now. Thank you very much. And next we have technology, or it's actually a transition function. So we call it education production function, but it's really a transition function from the parents' input, monetary, and time in early childhood, or depending how you want to model it here, we will have for 6 years into final education. So what would happen here, we're not modeling the middle years. So, in the first, I can show you in the application, hopefully, why. In the first 5 years, we would model the time investment, and then luck occurs, and you have some education. And given this education, what we will add is that you will have some ability that is also determined. So, but in general, this is a mapping from parental inputs in early ages into the state variables before you become an adult and start at the beginning of the life cycle. So, so ZT plus 1 includes, at cap T, the parents, that's it, they stop making, they die, and then the kids' generation start. So at the cap T plus 1, what is it? It's all the ZT plus cap T plus 1 at the end of the life cycle of the parents. You have the choices, characteristics of the parents, which would be education and some ability, and time input, monetary input, and siblings and ages, okay? And that's what we would need for the transition or production function or transition function of human capital across generations. And so let me start introducing the dynastic model, and then I'll go backwards and talk a little about the discrete choice. But this is the structure. So it looks like a Barrow-Becker model. And let's say I0, I0, and C0 are the optimal choices. And U1 KT is the per period utility associated with the choices, right? And U2 plug the optimal consumption, right? So it's only going to be a function of ZT. So I'm going to divide the problem into two parts. So the first equation that you see, it's UG cap T of X. So at the beginning of life, right, you are endowed with education and some ability, and you start your life, and your life will last for cap T periods. And generation G will be able to drop it off later. But this marks the life cycle utility. So this would be something standard that you've seen for discrete choice, dynamic discrete choice model, right? So whatever at time 0, whatever information you have at time 0, given your characteristics, you're just going to maximize. This is just expectations of life cycle utility for the life cycle components, the finite component evaluated at the optimal choices. So this is just for to present first the dynastic part. So let me put it inside the life cycle inside the Barrow-Becker-ish type model. So beta is just standard time preferences. And this is how, so at time T, so if you look at the second, so UG of X, okay, now this is the first part would be just the life cycle part, okay? So the total expected, utility when you start your life would have this component for your own life cycle. And beta is just the standard time, period by period time preference parameter, discount factor. So you are discounting, right, the next generation utility to the beginning of your life. That's why you have beta to the power of T. Now, what is lambda? Lambda is how much, think about, suppose you have your one kid. Lambda is how much you value the utility of your kid versus your own. So if you look here, so this looks like a Barrow-Becker. This is expectation of time T, but n to the power of minus nu is just the concavity number, n is number of kids. So you have diminishing marginal utility from number of kids. And then I'm summing cap it from kid 1 up to kid n, the utility, and you're just summing the utility of your kids. And right now we don't have gender yet. X prime n is your kids' beginning of life characteristics. So that looks like a Barrow-Becker formulation exactly, except that the UGT is a life cycle model within it. So we're going to be able to estimate all the different utility discount factor parameters, right? We will estimate beta. We'll be able to estimate lambda, and also nu, like, how much
in the slide, you have the discount factors lambda times n times 1 minus u, but down in your other lower equation, you have lambda times n to the minus u. Is that just a typo, or am I misunderstanding something?
Oh yeah, no. Sorry. So in a different version, I could do the following. I could write instead of 1. So what I have. So this thing is correct, but I could also write instead the average, right? I could write sum it up divided by n. So I could write it as the average utility, and then I would have n to the power 1 minus nu, which look a little bit more intuitive.
Okay.
But you're right, yeah, it's a bit yeah.
Okay, I get it.
Yeah, I think in a previous version I had like it written as an average utility.
Okay. Oh, I see. Yeah. I see.
So this is what we want to be able to estimate, and you could already see that it's a very big object because I have 17 choices. Life cycle, fertility, we're assuming from age 20 till 46 you make fertility decision afterwards. So it's a big model. And so let's go back. So I just plugged the optimal decision. Let's go back a little bit and talk about the optimal choice. So your state variables are ZT are the systematic ones, and epsilon T is the IID shocks. These are all, yeah. So the value function, right, is just max. This is standard, right? Max over max of, which make the optimal discrete choices. And this is just summing up the life cycle, right, from T plus 1 up to cap T. And then you're summing up over all the choices, discounted. The per period utility, both of the consumption and the non-pecuniary benefits from the choices is just called UKT. And then you add, so the only non-standard part here is that you had now the next generation, right? And of course, the next generation has the next generation, right? So it is an infinite horizon model. And you can write it still as a Bellman principle, as a Bellman function, right? So a Bellman value function. So you would have, again, maximum of it. This is a function of your shock. You maximize I, your choices. You have U plus epsilon, which is the per period. This is today's utility, beta, expectation, the value of next period. And then you have the transition function. I'll talk later about the expectations and the transition, right? The expectation and the transition here are more complicated because you have the standard period by period transition within the life cycle. And then you have the intergenerational transition function. And then you could write it as the expectations as integral over the epsilons. So I don't have any aggregate uncertainties right now here. And this is still fairly, look like fairly standard formulation. And the transition function is just state variable ZT plus 1, conditional on ZT, and the choices. And notice that the state variables, experience, time with kids, fertility, once you make the choice, it's deterministic. the evolution here of the state variables. So again, the goal of here, so my goal in this part of the talk is take this problem, okay, knowing that in the V, right, the continuation value, I have this, another object that has infinite horizon problem, and I want to write it as I want to write the representation that looks like a Hotz-Millerish representation that I could map conditional choice probability to difference in, to primitives, the differences in conditional valuation function into the primitives of the model, which is the CCP's transition function, the discount factors, and the utility per period utility function parameters. So I will write now this is the conditional valuation function. Okay, so conditional on K, net of the shocks. So your systematic choice variables are ZT. So suppose you choose K today, then your utility today would be net of the shock is UKT, and then plus beta. So you made some choice, and then from next period on, you're choosing optimally, and that this is just a continuation value and the transition function. And then the conditional value function is the key component to the choice probabilities, right? So the optimal decision, which is a function of the state variable, would be argmax, right, of this conditional value function plus the shock. Okay, so this is discrete choice. So even if we have a lot of choices, we just compute them, and then we choose the max. So the model valuation function gives an implicit function defining the ex ante value function only as a function of primitives of the model. And this is what I want to show you. I want to show you how. So let me define again, what are the CCPs, right? They're the expectations, right, of the optimal choice for every systematic vector of state variables. So now I'm going to write V of ZT, right? So V of ZT is the ex ante, right, value function, right? Before you see the shocks, you just know ZT and you write it. And I could write it in terms of the CCPs, right? And again, this is so far a standard, and you've seen it in previous lectures as well. So this is from K up to 17. So these are just the choices. We have PK of ZT. These are the CCPs. And you have today's utility, which is UKT plus the expectations of the shock, conditional on the choice. And then you have beta plus the continuation value, conditional on your choice today, and ZT. So far, this look still fairly standard. And so again, I've already shown you so I could write the conditional valuation function net of the shocks is today's value function plus this value, which, function, which I just defined in equation 5, right? And what do I have here? Next period state variables conditional on the choices and ZT. And again, conditional on the choice, in this example, the state variables evolve deterministically. So we want to write, wait, did I go? Yeah. So I'm getting closer to the representation. So I have the optimal choice, and I define it again as argmax of the sum over IKTs, whether is a 0, 1, right? Whether you choose, a combination of choices, and this is the utility, the conditional value function that is attached to it plus the shocks. And then I'm going to write the CCP. So this is a definition of PK but just this is standard, so you've seen it in discrete choice, right? So integral over the optimal choice, right, is just going to be 1 if the differences between, right, the value function of choosing k is better than the choosing k plus 1, k prime, given all the shocks. And what I want to remind you is that if I look back at this problem, let me look at, before I move to the representation, if you look at equation 1, so the part of the life cycle without the U generation, right, we have like Hotz-Miller representation, right? So for the life cycle, we know how to get the differences in the valuation function only as a function of conditional choice probability, transition function, and the primitives of the model, right? And the utility and the discount factors. So what the hard part is just this UG that hits you at the end of the life cycle. So let me, before I go to the, so now I want to go to the ex ante value function representation. So let me write the initial value at the beginning of the life cycle, okay? So I'm writing exactly this equation, okay? UG, right? The second equation, UG of X, okay? So at the beginning of the life, so the thing is that X is discrete, okay? So you have education, and we will have some ability, and we will discretize it. So you would have types, okay? And I could list the type. It's going to be integers from 1 to X. So all I'm doing is writing the value function at the beginning of the life for the different state variables that you start with. I'm just writing it in matrix form. So I have V1 up to Vx, right? And then I have U. What is U of k? U of k would be the lifetime utility, okay? Just the life cycle component, right? Associated with the choice k. And again, I can write it just for every possible state variable at the beginning of the life cycle, right? Because you still haven't made any decisions, and there is no choices to carry. And this is expectations of the shock, right? If you make a choice k. And these are the choice probability over all the possible choices at the beginning of your life. I is just a vector of, it's just identity, just ones. And this is important. So M0K, this would be the intergenerational transition function from every possible state today, okay, at the beginning of the life into the next generation. So this is all you've seen. I'm going to show you the representation, but I just stacked it up in matrix form. And I think this is a bit out of order. So let me start. I'm going to go a little bit back and forth. So let me tell you what I want to do. So I show you this matrix form. What is the purpose of what I'm going to do? So let's look at VK. Ignore the bottom line for a second. So we have VK, right? So this is the conditional choice net of the shocks, and it's a function of today's utility if you choose KT, right? And this is some of the CCPs, right? Expectations at time t, utility plus epsilon shocks, transition function that is defined recursively FK. And then I have the component lambda, you have lambda, beta, n, right? So, and then you have the dynastic component, okay? So the first two lines, I know how to write this, differences in valuation function in just terms of the primitives of the model. So my goal is, the problem is I have V of X here, right? In the continuation value. So this is what I'm trying to to get representation for. Okay, so let me go back to this. So I defined that, and the slides are a little bit out of order. And I'll go. So this is what we're doing, right? That's my problem. Let's take the value function at time 0. Okay, in this is I think the punchline of the first paper. Then I could write it as the sum, the expectation at time 0, right? I have CCPs, and now what do I have? U of k is the life cycle utility, okay, within a life cycle. Expectations of the shock given action choices combination k. And what do I have here? Lambda, beta, right? The discount Barrow-Becker type discount factor. This is a component-wise multiplication. And this is the transition function across generation that takes me to next generation, V0. So I'm assuming stationarity. So you could already see I have V0 on the left-hand side, on the right-hand side. So can I invert that, right? If I do that, I'm pretty much done, because that I know how to deal with the life cycle part. So what do we have? So I just rearrange that, and I have Ix here, right? And the question is just to show really that V0 is invertible, right? And it has, and you could show that it's actually invertible. So let me go back to another slide. Okay, so you could show that this is you have dominant diagonal property in this, and you could show that it's invertible. So what we've done here is really we're just combining results from previous literature, like Aguirre-Gaviria and Marira and Passendorfer. So you have results from infinite horizon models, and then you have results from finite horizon model. So what we've done here is really combine them together, and we got the representation. So really that's the key to get the representation. And now let me go back to the proposition. And this is what I want, right? So to get the Hotz-Millerish type of representation, I have VK, right? And now I know that I have Vx, but I know I can write what is Vx, by the way? X is a component, right? It's next generation utility. X is just a component. V0, remember, V0 was a vector, right? So it was, X is a component of V0. And really, that's given that we can have an inversion here, we could really get it into a representation like a Hotz-Miller representation. And I get now, I can write the differences in the conditional valuation function as a function of the primitives. So really, that's the whole key of how do we estimate this type of models. And so sorry. So then, how much time do I have? 45? 30? Okay. So I think the next thing. So I think the next thing I want to do, so I could show you, this is a generic estimator, and we have some comparison of different estimators, but instead I want to actually use this representation and go to a full-blown application. And you could see, so just having this representation, you could actually estimate really large structures. And so this is what I'm going to do next. So I already motivated it. So the application is going to be, we've seen that there is, I don't even know, there are so many papers who run regressions, right, of parental incomes, right, child income on parents, right? So it's the intergenerational correlation. So it's a standard way people measure persistence or mobility, and and what we want to do is actually find a mechanism, right, of what generates this correlation. Okay, what really caused the income, this correlation or lack of mobility or high mobility. So there is a growing literature that is looking at the mechanism that that generates mobility or lack of mobility and persistence of income across generation. So here's what we're going to do. So the model should go fast. So until now, I only had a genderless model. So I'm going to add gender, but I'm still going to have a unitary household. So the causes of correlation across generation, what are they? Parents' education, and you can call it ability or skill, okay, is going to be fixed effect in labor market. You can call it nature, although it's not really nature. And you have investment, monetary, parents' time when children are young. And what is going to affect, so the problem is investment is, so you have a lot of papers that try to get the causal effect, but the point is that if you think about policy, investment is a decision, okay? So in order to evaluate policies, you want to know, is the policy going to crowd out parental investment, or so you want to model behavior. And you want to understand, but in order to understand, hopefully I'll have a little bit of time to convince you with data that to understand household decision of fertility, time allocation, and specialization, all these are going to be crucial, if you want to understand how much time, parents are investing in their kids. And before I do that, I should convince you that time with young kids matters. What we're going to find here is that the earning structure in the labor market is key. And but another, so you have markets here. We don't have marriage market, we only have labor market, but labor market is important. Another key is assortative mating. So the different types of households by education here are going to make different types of investment. So we want to understand that. So all these are going to be possible sources of correlation in income across generation. And if you notice that when you have a full dynastic model where the utility of the kids is in the utility of the parents, when parents make investment, they also care about who their kids is going to marry when you start adding assortative mating and gender. So part of the return maybe to get college education is what your spouse, who your spouse is going to be. So another thing is that we can use, because we have stationary model across generation, we can use 2 generation that we link in order to estimate this model. And we're going to use here the PSID from 68 to 96. And we have 2 generations. They're not really separate generations in terms of time, so we have kind of overlap across the generations, but it's parents that are linked to their kids. And we are going to use the discrete framework. So we're going to use time with kids. We're actually going to use household work. So we normalize the data. It's been done in the literature because it's not just time with kids. To some extent, it's not incredibly important to us. I'll explain why, but it's a transition function from time you put in kids and in the household relative to how much is a residual, this term. So relative to how much time you put in your kids when you didn't have, when you given your education and your characteristics, you look at the gap between how time you spend on housework before and after, and you attribute it to time with kids, basically. We've done a lot of validation with the CDS and the ATOS to see that we get reasonable patterns, and we do, although the time frame is not really overlapping. And so this is going to be in this application. So of course, time with kids depends on the education. So in this sample, we only have, so tomorrow I'm going to show you single parents household. Here is just married couple and fairly stable married couples. So it's relative, it's not a representative sample. And you could see our measure of time with kids, and you could see that college women are putting, this is annual time, the most time with kids. Women put a lot more time with kids than men, and this is in the first 5 years. So that's basically what I wanted to say. And of course, sorry, and another thing is that, labor market hours is important. So why are labor market hours are important? Because if you work a lot, then you might have higher this utility of spending a lot of time with children. And you could see that at labor market hours, so college, actually women with some college work the most, and men with college education work the most. So we're going to actually find the time with kids of fathers matters, although you could see that quantitatively there are real large differences between men and women.
Isn't there this relationship where richer, more successful parents spend more time with their children? Is that you see that in your data?
Yeah, but they have less kids.
You know, they should have a higher opportunity cost and not one, but they actually spend more time with their children than lower income parents.
Yes, it's true. But what you would see is that they have less kids, or the spacing. So what happened, we actually model spacing.
Oh.
So we're looking at time in the first 5 years. So it matters if you have like 2 kids under age of 3, or you space them, or you have less kids. So that margin, so we're going to look at quantity quality trade-off, so to speak, and it actually plays a big role in explaining what we see here.
Okay.
But yeah, that's right, because, you know, quality, like education and quality of kids is a normal good, maybe luxury goods, right? So, but you have the time constraint. And what I forgot to actually mention is that the original Barrow-Becker has this neutrality results that actually richer people will not have, you know, richer kids, because the demand for kids is also increasing with income, right? So one thing that is relaxed here already in Lowry, but without endogenous fertility, is that you have the time constraint, and you have correlation, and you have non-separability of budgets over time across generation. So that's exactly, so that actually really works there. So it goes, so in the cross section, there is negative correlation between wealth and fertility. But the quantity quality trade-off, you have opportunity cost of time, right? And but there is the wealth effect. So these are the things that are going to happen in the model, right? So on one end, you want higher quality of kids, but time is limited, right? If you are you have high potential earning, and that kind of is going to be balanced, but the increase in demand that, you know, that still works in the original Barrow-Becker model. And more educated people, women spend more time with their children despite the higher opportunity cost of time. This is just observed in the data. So the trade-offs are actually, so it suggests that there are involved trade-offs in this model, right? To, you know, that are needed, that you need to understand in order to figure out the observed correlations in the data. So you've seen the model. So let me we just added gender really. So again, this is the timeline. So we have early childhood, late childhood. So in this model, so kids don't do anything except consume. And in early childhood, I'll show you data, at least in this application, why people put time and money, and then there is passive monetary investment that depends on your household characteristics. And the time TE, what's important in this type of models is that there is going to be a time where fertility ends, and then you could still have 5 more years to put in your kids. But what we cannot allow is that you would have one kid that is an adult and you're still making fertility decisions or investment in time, or time investment, because it creates a lot of strategic consideration. And I'm not even sure that there is a solution to the model. And then you have consumption, birth, time with kids. Then you would have period where you are not fertile and you still invest in kids. And then a period where you just work and consume. And then at the end of that, your children's life cycle starts and that's it. So it's the same model that we've seen before. The only thing is that we have male and female children. So your utility from the value function for a female and a male may not be the same, okay? And we have a matching function. So these are the things that I added, right? So we have G would be a matching function. So you start your life with characteristics X, right? And given your education and actually your ability, you're gonna match with somebody, okay? And here there is no divorce. And tomorrow we will have all this endogenous. Again, now we have a household, but it's a unitary household. So you have male and female. And what is a female in this model? Well, the labor conditional on education, women's earnings might be different. There might be a tax. We're not trying to model or explain why, but we allow it. And also this utility from the utility from different combination of choices is allowed to be different for men and women. And lastly, we allow for the transition function, we allow for the effect of time of women to be different from the effect of time of men. So these are the three different channels how we model men and women here. So, the same notation, except that the household labor supply would be a vector, right? With choice of hours of men and women, and birth would be 0 or 1. And the same time with kids, you will also have low, medium, and high. And we discretize it differently for men and women because the distribution is so different. Wages are the marginal product. And again, you would have age education profile, right? So there's going to be returns to education that vary by age. There's going to be experience. So experience, so we're going to, John asked earlier why we carry choices. So we will carry the last 4, I think, years of labor supply. The reason is that afterwards is not significant, but experience would matter. And we will have, so we have some form of unobserved heterogeneity, which would be, except for the IID shocks, and that would be individual specific ability that affects the labor market or fixed effects. And so what's interesting is what is this intergenerational? It's really a transition function of education. So here's what it is. So, and again, we allow it to be different for men and women. And in fact, we will find that conditional on inputs, women are always doing better. And I think there are evidence in different, in different types of data set for that. So it's a function of the characteristics of the parents. So X of the parents here would be their education of the men and the woman and the fixed effects of the parents. That would be, nature, although it's not really nature, it's actually endogenous in the model. And then we have D from 0 to 5, that would be the time investment in the first 5 years. And wages, so we'll put household income in the first 5 years. And number of siblings under 5. And omega is luck, okay? So F and M is for male or for female. So your parents invested, then, they have some characteristics, they put some investment and they earn a certain amount of money, right? And then there is, you become 18 and there is, or 20, and then you get your education. once the education level is determined, so this is the fixed, how the ability is determined. So what we're assuming, it's a function of your education. So the investment of the parents and their characteristics affect your fixed effect, but only through education. Where actually it's not necessary for, it's actually not necessary, but this is how we estimate it here for here. And then you get a shock. So this is the transmission of ability. Budget constraint is the same here. You plug it in the preferences. So I've shown you all of that. And what are the sources of uncertainty and the shocks in this model? So relative to what I've shown you before, which was the IID shocks. So we have the matching probabilities, right? So it's still, you know, you have education and actually ability. You could do matching on that too. But then there is, you know, it's stochastic function. So who you marry is stochastic. The preference shocks and the educational outcome and the innate ability. So these are the only sources of uncertainty in this model. And so the timing of the choices we've already gone through. You see your preference shocks for the household, and then you make for the household fertility, time allocation, meaning the labor supply decision, both for the female and the male, and the consumption decision. So let's look at the valuation function. And again, this is altruistic household. So we've seen it. So now I only added male and female. So the state variables, F are the state variable of the female, and M is the state variable of the male. So the utility, this is actually generation here, so I apologize. And we have the values of VI of F and M is the life cycle component for the utility for the male and the female. And then you have, again, we've seen it before, right, on the previous set of slides, the same discount factor. And this is what John asked. I wrote here, instead of writing n to the power of minus nu, it's just the average, you know, I can just average the utility over all the kids and write n to the power 1 over nu. But it's the same too. But now we're going to, it's going to matter whether your kid is a male or a female. And so it's a little ugly. You could see what U bar is like the average over all the males and all the females, the kids that you have. And this is your utilities from their household. So you have F prime and M prime. And the life cycle at the optimal choice. So we've seen that, right? So it's expectations. This is V. So expectations when you start, you know, when you start making decision, T is childhood ends, and then you start, this is the life cycle utility. So, and it's identical to what we've seen before. So we've seen how, so this is a model that we've estimated using exactly what we've done before. So we're solving for stationary equilibrium. And we're going to see, again, endogenous fertility, and what's going to affect it. We will have wealth effects that will imply positive correlation between fertility and education, but then you would have quantity quality trade-off that there is opportunity cost of time that is higher for more educated people. And what's in play here is the household specialization. Why do women spend more time with kids, right? You've seen it in the data. And why certain households have different fertility and different investment patterns in kids, and so I want to know how assortative mating is going to affect the investment decisions. So educated men are still more likely to marry educated women with high opportunity cost of time, but the question is, are these women just more productive in producing high quality kids in the production function, or is it something else? And and here, so I started by saying we have exogenous gender pay gap, but that can affect the specialization patterns in the household, right? Because the opportunity cost of time is going to be different for men and women. So here's the estimation just in steps, because you know how to do it. So how do we estimate a model like that? Okay, so it's a huge model. So step one, what do we do here? So number one, we estimate the earning equation. And I told you that I added unobserved heterogeneity in terms of fixed effect. And the way we do it, we just have log wage difference regressions, right? So we just have fixed effect regressions. And we're actually going to estimate in the first step, this unobserved heterogeneity, and then it becomes observed. Because the problem is that the conditional choice probability, everything, you know, it has to go into the decisions. So that's already Altuk and Miller in 96 did that. So this is how we add some unobserved heterogeneity. So we start by doing that, and we're estimating the CCPs and the intergenerational transition function, but that's tricky, right? Because I need to estimate this education production function outside the model. So I'll say a little bit how we do that. Basically, we're doing three-stage least square, right? We have exclusion restrictions, I'll tell you. But all this has to be estimated outside the model, so it's not cost-free. So you have to figure out how, you know, a way how to do that. Step two, we use the representation. So we have, what do we have from the first step, right? Remember, we have the CCPs, we have the transition function, we have observed, everything is observed heterogeneity, right? So now I can write the differences in the valuation function, right? In terms of just the utility function parameters. And once I do that, because the life cycle is non-stationary and I actually don't have a finite state dependence, which I know you learned a couple of days ago about, then we can use Hotz, Miller, Sander, and Smith. So we form moment conditions from the CCPs and estimate the structural parameters. So in the third stage, or it's really a second stage, but we use you know, you could use GMM. So we just estimate the discount factors and the per period utility parameters. So that's the. So let me show you a few interesting things about the estimation. Well, the wage gaps by education, we know that they're there. But one thing that is interesting is, I won't show you tables. I want to show you a picture. So what is this picture? So the first panel is the age education profile, right? Remember, I had like a fixed effect regression. So I have education is fixed. So I interacted with age. And you could see the top line is obviously the wage growth over the life cycle of the part in the, this is just plotting the estimates from the earnings regression, this part. And you could see that it's much, much larger for college educated individuals. And there is some college, and then there is high school. And the second part is interesting. So what's going to matter here is in fact experience. So we look at the experience in the first, for 4 years. And it matters, so we allow it to matter whether you work part-time or full-time. And this is what I draw. So this is 0, and what you see, the graph in the second panel is negative. So what is it? It's the penalty of working part-time versus full-time separately for men and women. And this is at age 25. So you started age 25, you work part-time, it started 0. After 1 year, you could see already that the penalty, the red line is for women, right? This is how much they're penalized for having a year of experience of part-time versus full-time, but you could see that for men, the penalty is larger. So of course it could be occupation and things like that, but in the model, it would play an important role that withdrawing from the labor market would have a dynamic effect, and the dynamic effect is smaller for women. So this is part of it. But it would turn out to be more important than we thought, this dynamic effect of the labor supply. Okay, so this is the 3-stage least square. So we have three equations, okay? Why don't I show, well, okay. So let me show you, this is just a linear, right? So the omitted class is less than high school. So we have college, some college, and high school. So these are just probabilities. But let me tell you how, more importantly, you could do some more sophisticated things if you want, but actually the main results remain. The problem is that you have simultaneity. So remember what's in it. So we have the total, when you start your, you have the total labor earnings of the parents in the first 5 years, the amount of time that each parent put, and the fertility. So you have a standard simultaneity or endogeneity problem. So we have a system of equation just with education, labor supply, income, time spent with kids, and fertility. What are the exclusion restrictions here? So we're using the sex composition of siblings with all the whatever caveats you have. So what's the exclusion restriction? We're assuming that, suppose you have 3 kids. So composition means do you have 2 girls and 1 boy, or 3 boys, etc. So it's going to affect parental time and fertility, but it doesn't affect labor supply or the education production function directly. Okay, so this is the exclusion restriction. We're also utilizing the age earning profile variation by education, sort of a quasi-experiment in income, labor, and subsequent fertility. What it means is that we're assuming that given your time, parental time with kids, okay, your age doesn't matter. It would affect your labor supply, and through that it would affect it, but it's not affecting it directly. So okay, I want to go to the results, and I don't have that much more time. So let me. The education production function is interesting, but by the way, so how much do you like your kids? Points relative to your own utility, 0.795. The discount, the new is 0.1. So that means that relative to the value of the second child relative to the first is 0.68, and the third is 0.6. And also we have the cost of kids or net utility while they're in the house, and it's actually cost. That's so the utility is negative, but it's mixing up. We don't observe actual expenditures, so it could be money expenditures, but it's net utility that were identified. But this is the last thing is going to be important. The cost as a share of the household income decline in the education, not the level, but the share of the cost. What does it mean? It actually captures the increase in demand when your income is higher for educated people. There is also increase in demand for number of kids. It's coming through this channel in our reduced form. This is how the decisions are being, this is the fit of the model. But let me show you what are we doing. So correlation, so now regress log wage of your kids on parents. You could do son, father, we did all of them, father, daughters, household, parents' household and kids' household. But it's not a moment in the model. It's not a fundamental moment. So we're just seeing how much we're matching it, right? So we have our model. You could, you can simulate your data, and you could compute what your model would predict, which is I don't know, 2/3, depending on which part you think. So that's what we're trying to replicate. But more interestingly, what causing it? Okay. So this is the counterfactual. So what are we doing? The first one, where we want to say, okay, we have the correlation in the model between parents' income and kids' income. But what I want to know is what channel matters the most. And we do the following. In the baseline, we eliminate the dispersion of parents' education. So we assign the same education for everybody. I didn't show you the production function, which is key, but parental time matters a lot, both for women and for men in a different way. So mother's time increased probability of going to college, and father's time truncates the bad outcomes. So it reduces the probability of not finishing high school and increasing the probability of some college, but not much for college. And it's large actually, the effects. We do not find that actually more education matters, but we do not find the time and education interaction add anything. So it's actually, but the education is direct effect, obviously. So we assign high school for everybody. Then we simulate the model and we just compute, right? And then you could run a regression and compute what would be the correlation. And then spouse matching function is set to be uniform with equal probability for each person to marry a spouse. So we kill the assortative mating, okay? So everybody marry everybody randomly. The earning equation is set so the compensation doesn't vary with the age and experience. So now there are no returns to experience. 4, returns to full-time and part-time. So we set it so there, I didn't tell you, but the returns to full-time is more than twice the returns to part-time. So we put it to be exactly twice as much. And number 5, the direct monetary cost of raising kids. We kill the education gradient of the parents and the demand for therefore the increase in demand of richer household for kids. Sorry. Wait. So here's the main result, because I have to finish in 2 minutes. So this is number 1. So this is different types of correlations, the bars, okay? But these are the counterfactuals, and I don't know if you could see, but 1 means that this is the correlation in the data and how much each component, right? Each counterfactual explains out of this correlation. So of course the initial one creates almost nothing. Assortative mating explains almost nothing. It's counterfactual 1, okay? Of course, I'll talk about the order in a second. 3, the age, the education gradient in the earnings doesn't explain anything. You could see already that the first important part is counterfactual 3. And what is counterfactual 3? It explains 60-something% of the correlation, and that's the experience. So the fact that you have a dynamic effect of labor supply, and I want to talk about why in the model. So I'll do that. If you add full-time, part-time, you're shooting up and getting like 40% more than the correlation that is observed that our model predicts. The second interesting part is counterfactual 5, where we kill the demand by income and education, or by education to kids, and you could see that reduces the correlation a lot. Why? Because you kill the fact that it really reflects the fact. I'm sorry, we bring it back. We bring back the variation in demand by education, which is the opportunity cost and income, but potential income. But what happens is that it shows you that the increase in demand to kids is really playing a role here, and without it, the correlation is much because of it, the observed correlation is actually a lot lower. But I want to focus on why, and that's how I'm going to finish. So why experience? What are the trade-offs and how it works in a model? So it accounts for 61% of the observed persistence. So what happens when you bring back experience? So female labor supply of full-time work increased for most households in which both spouses have at least high school education. But the key is that fertility is going to decline But the largest decline is for the household in which both spouses has at least some college or have some college or college education. And this is really the key factor. So then mother's time for kids with per kid increases at a higher rate in higher education household. So the average mother time with kids decline in household in which mothers have less than high school education. Father's time with kids also increase in high education household and declines in household in which both parents have high school or less. But it is the decrease in fertility of well-educated household together with this quantity-quality trade-off that really causes the persistence. So really like one key here is that the structure of the dynamics of experience, and then of course full-time, part-time, really increases the fertility. And I should stop here, right?